really nice to see such a diverse group of people and some very, very old friends. Not old necessarily in age, but definitely in terms of friendship and alliances. And it's lovely to have you on the meeting today. So I'm just going to start off by welcoming everybody. I'm assuming you're here because you want to find out more about what we're doing on the Open Source Satellite Programme. We'll be talking today about some open source space approaches. We'll also be talking about some of our upcoming projects. So there are opportunities for you to become an active contributor on some of our projects. You might already be involved in some, or you might want to get involved in others that are up and coming. You might be considering being an early adopter of the spacecraft design and wanting to find out more about what the design is capable of, the kinds of missions that it can support. Or you might want to join in one of our Designathons, either as a participant coming up with solutions. You might want to mentor a team or an individual that's working on a Designathon, or you might want to be a judge and help us to decide who's doing, who's got some great ideas that we should be celebrating and recognising. So there are just a few ideas there about ways that you can get involved and ways that you can find out more. In terms of what we're going to be going through today, I'll go through a quick intro to what the Open Source Satellite Programme is all about. And then Vicky's going to give an overview of some of the structural and mechanical developments that we've been working on. And then we're going to pass the mic over to the CFMS team. They are one of our commercial and organisational collaborator teams, and they've been doing some optimisation work with their heavy compute power and processing power to look at how you can do multi-object optimization to come up with an optimized spacecraft structure. So James Osborne and Davide Bianchi will be talking about that. And then we're going to move on to one of our individual collaborators, and he's been doing some work to develop a model to evaluate different launch vehicles, and so that you can down select the appropriate one for your mission. And then we have Paul Madel, who's one of the KISS team also. He's our software lead, so he's going to be talking about some of the software development work and also talking about some of the recent results from our radiation testing campaign that we've been doing to down select candidate microprocessors to form the beating heart of the command and data handling system for the Open Source Satellite Programme. And then if we've got time at the end, Vicky is going to give an overview of some of the systems activities and highlights, and we'll do a wrap up. And if we've got time, we'll answer some Q&As, but I and a couple of the others are happy to stay on for a little while beyond the 5:30 BST cutoff. And you can always ask questions in the dialogue, and we can get around to answering those separately as well. So I'm going to start by saying what an exciting time it is to be in space. I mean, it has been for those of us who've been in the industry for a while, but when we look at where the next disruptors of the industry are going to come from, we believe that it's going to come from the convergence of open source and space together. And we've written a couple of positioning papers over the past year where we've talked about how the similar constraints that have driven open source development over the years in terms of software, computing and the maker movement, and moving into putting things like Raspberry Pis in space, how that kind of movement that's been looking at how you can improve affordability and accessibility, how those kinds of influences have been very much repeated in a separate stream of development on the spacecraft side, from the very first satellites that were launched back in the 80s through to what we saw at Surrey and helped to initiate at Surrey with the small satellite revolution, and seeing where that went to with CubeSats as well. And so those two separate strands have been coming closer and closer together and are now at the point where they're converging. So we've seen the first open source mission results with some open source CubeSats, and really the genesis of the open source space community. And there are a lot of different activities going on in open source space, all the way through from teams who are leveraging open source data that's being generated, Earth observation data, through to teams that are building subsystems and full spacecraft and looking at how we can do missions. And of course, the ground segment side as well, where a lot of people have been able to get into open source through leveraging assets that already exist in space. And it's a really great time for this to be happening, because at KISP and in a number of other teams, you know, we're very cognizant of the challenges that exist in the small sat market, and a lot of it hinges on the business case challenges. In that, you can see in this top left-hand corner, we've got this S-curve showing some of the business case challenges, in that development time for spacecraft is always longer than we think it's going to be. System costs are generally very high, and it takes a long time to recoup your money at the back end, because you've got all this capex at the front end, and it takes a long time until your mission is in orbit and you can start to generate revenue and return on investment. And when you start to tap into where those development costs are coming from, a lot of those mission costs are coming from labour. Labour costs constitute anywhere from 50, 60, maybe even 70% of an overall mission. And a lot of that comes from NRE, non-recurring engineering, and the touch time that's involved in integrating lots of black box systems together. And then when you look at where the CubeSats and small sats and traditional satellites sit, they're generally along, you know, a continuum of price performance. And what we believe needs to happen is, you know, a move away from that curve, move away from that line, to the point where we can achieve a 10 times improvement in price and performance. And those are really some of the challenges that led us to thinking about, well, how can we solve this problem, looking at how we can use open source as a way to do this. So we are in the process of developing the next generation microsatellite platform. Some of the top specs are here, and if you want to find out more, we've got lots of papers that we've written, and we can share the links of those with you. So we want to develop a next generation microsatellite platform that's capable of supporting missions from 25 kilograms to 250 kilograms across a whole range of different missions and services and applications. And as I say, to provide a 10 times improvement in price and performance. So that's going to solve the price performance problem, but it's not going to solve the accessibility problem. It's still really hard for people to get into space and get hold of space technology, even though CubeSats and small sats have done a really brilliant job in reducing some of those barriers to entry. So that's why when we've generated and developed this next generation microsatellite platform design, we're going to release it as an open source design that's freely available for anyone to use and take and modify if they want to, starting from a really solid, stable baseline, and use it to develop their own missions on. You know, I was interviewed by a reporter a couple of weeks ago, and I kind of use the analogy that I want the next generation microsatellite platform and the open source satellite system to be essentially like an iPhone in space, you know, with a lot of capability already built in, and you build your apps on the top. So that's where we want to get to with the open source satellite program. I'm going to stop there, because we've got a lot of interesting talks still to follow on from this. But if you'd like to know more, do get in touch with the team, and I'm happy to share further details of what the design is going to look like, what we aim to get out of it, and some of the philosophy behind the open source satellite program. So at this point, I'm going to hand over to Vicky Anderson and stop sharing, and she's going to move on to a conversation about structure and mechanical developments.
Oh, so lovely. Thank you, Anita. Now let me just pull up my screen. Bear with me a moment.
Hopefully I've stopped sharing.
Yep, and hopefully you guys can now see mine.
Yep.
Lovely. Right, sorry, bear with. Okay, cool. So we're going to talk about all things structural, and for me, kind of the structural stuff is quite interesting. I mean, it's all quite interesting, but the structural stuff is especially interesting because kind of open source, when it comes to kind of mechanical and structural things, I think is quite a different concept. You know, we talk a lot about open source software, but you know, kind of moving towards that open source hardware domain is a bit different. And I say it's proving some interesting challenges for us, and ones we're hoping kind of the community can help us with. So now we're going to sort of go through kind of all things structural. So I'm going to talk very briefly about our structural concept Designathon that we have, and then I'm going to hand the floor over to a couple of our collaborators who are going to talk about some of the things that they've been doing. So just starting off kind of briefly, kind of what is it we want from a structure? So it's, just a small thing. We want a scalable modular structure that you can use across a full range of satellite classifications, from 25 kilos to 250 kilos. It's simple, right? But we're aware there's some challenges there, and it's not not quite as straightforward as getting the Meccano out and building different ones. We want to service a number of different applications, as Anita said. We want to better make this work for an Earth observation mission, where you want to be pointing down, looking at the Earth. We want to make this work perhaps for an Internet of Things application, where kind of the payload you want to put on top is quite different, and those all have very different challenges in terms of what that structure needs to look like. I've talked already about the mass range. A 25 kilo satellite is probably going to look pretty different in size and mass than a 250 kilo satellite. So how can you make common things that go across those full ranges there? Different launchers. Rich is going to talk about this in a bit, but we've got launchers that are vertical launched. We've got launchers now which have that horizontal component, and we don't want people to be limited by by the launchers they can use by our design. We want people to better stick this on any rocket that currently exists and any rocket that comes along in the future. And as Anita talked about, cost and reducing touch time, manufacturability and costs are massive pieces of this puzzle for us as well. Some of the biggest costs comes from us having to actually kind of do hands-on work with the satellite. And although I don't think we're going to be quite at kind of car production kind of robotic style stuff with this, we really want to limit the number of fixings, limit the number of kind of screws you have to do up and all those kinds of things, and make something that really is kind of low touch time and is affordable. And our solution to all this, well, it's very much ongoing, and that's why I'm kind of hoping some this might pique the interest of some of the guys in the community, and some of you might like to get involved. So we have this Designathon, and so this is your opportunity. Have you ever wanted to have a go at designing a satellite? This is your chance. We're really looking for kind of novel and innovative ideas of how to kind of put the core pieces of a satellite together from a mechanical perspective, and not having any space experience is not an issue. We've put this handy, I was going to say kind of grab size. It's quite a meaty presentation on kind of all of the things you would need to know about how to do structural design and what pieces you actually need to fit into this puzzle, into this kind of Lego block. And we're also going to put together a brief intro video, because I'm aware that the pack on its own is probably a little bit, perhaps looks a bit unwieldy to some, especially if you don't have experience in this area. So myself and one of my colleagues, Ben, is going to put together a video kind of giving a bit of an intro, and that should be kind of online by the end of the month, which we'll better share with you all. So we really want to look at kind of novel and innovative ideas. Are there things from other industries, like, I don't know, automotive or aerospace, that we could look to leverage and go, actually, this is a neat way of putting something together? Or we don't have to go with a box, maybe we go with a different shape, and all those kinds of things. So we're really looking forward to kind of kicking this off and getting some different ideas. And the reason I haven't put a picture on this slide of what we think the satellite could look like is I don't want to kind of predispose anyone towards certain ideas. You are going to see in some of the latter presentations some sample pad and things, but this is by no means kind of our fixed final solution, and we are looking for different and novel ideas. So what I'm going to do, as I really would like to get on to some of the other material that some of our collaborators have, is pass over to our colleagues at CFMS, who are going to talk a little bit about optimizing spacecraft structures. Cool.
So could we, next slide, please, thanks. So hi, I'm James, and I'm a space geek. Although I'm likely the most unsuccessful space geek you ever did see. I've only worked on hardware for one mission, and that failed. And I'm joined today by my erudite colleague Davide, who handles our advanced simulation team, which covers computational fluid dynamics and finite element analysis. Davide combines his passion for both of these in his favourite aerospace discipline, namely engineering aircraft toilets. We'd like to thank KISP and the OSSAT community for inviting us to talk today. I need to mention a few corporate bump bits before I hand over to Davide for the interesting stuff. So next slide, please. I'm sure many of you have never heard of CFMS, so wanted to give a quick summary of what we do and who we are. We're a not-for-profit digital engineering company established by Guarantee in 2007. We're located in the Bristol and Bath Science Park, and we have about 35 employees split across our 4 groups of model-based engineering, advanced simulation, data science, because everyone needs a data science team these days, and backed by our engineering compute team who run our Cray high-performance computer. Our principal industrial members are Airbus and Rolls-Royce, yet we maintain our independence and neutrality, which is important for our varied customers. And we participate in numerous Aerospace Technology Institute, Advanced Propulsion Centre and Innovate UK projects, and operate a range of commercial sectors, mainly in aerospace, but also transportation, construction, automotive and energy, to name but a few. And the next slide, please. As you can tell, I'm going quite quickly because I want to get to the exciting stuff. I need to mention some of our sponsors, the first being the Digital Engineering Technology and Innovation Programme, which CFMS is involved with. DETI is a 2-year programme sponsored to the tune of about £5 million by the West of England Combined Authority, with another just under 4 million coming from industry and the High Value Manufacturing Catapult. DETI is being led by the NCC with partners in DigiCat and the 3 regional universities you see on this slide there. Its aim is to help regional businesses adapt to changes in their sectors by adopting and evolving digital engineering practices, with COVID-19 recovery a critical addition after we launched. For today's presentation, the most important of the 3 packages is the enabling capabilities, which is mainly led by CFMS and is the vehicle for the work that we've conducted on the OSSAT. I'd also like to highlight the Skills and Workforce Programme, which is being led by the University of West of England, or UWE, which is about upskilling the workforce and conducting STEM outreach. And on that topic, if we could have the next slide, please. UWE are holding some inclusivity workshops and a seminar to discuss the results of those workshops. If you're able to assist with their valuable research, please hit the links up and sign up. We in DETI will be very grateful for your support. We'll be sending these slides out, I think, afterwards, so you don't have to madly copy down those links. And next slide, please, Vicky. Great. And the second sponsor, as it were, and my final slide is to talk to you about DOORS, which you'll hear mentioned later. DOORS is an Airbus-led programme which has been funded for 3 years by the UK government through the Aerospace Technology Institute, with the goal of developing advanced wing solutions for the next generation of Airbus aeroplanes. Within the consortium, CFMS is investigating several novel technologies, including the automated generation and optimisation of wing structures, which has supported the work conducted for OSSAT. And that's my cue to hand over to Davide to tell you all about it.
All right. Okay, next slide, please. Thank you very much. So a few months ago, we've been contacted by KISP to perform a multi-objective optimization of the OSSAT concept. The purpose of the optimization was to create a baseline structure to be employed for different missions and be launched by different rockets. Obviously, we had an overall constraint, which was do not pass the material allowables, do not break the structures. And we had as variables the different materials, the different geometry of the satellites, so the different overall dimensions and internal dimensions, and also the position of all the equipments inside. I'm going to go a little bit more in depth on this one later. Next slide, please. So the idea is to divide the satellite in 2 parts, the platform and the payload. The platform being the more generic part with all the controls of the satellite, and this should be pretty much in common to all different satellites for different missions. While the payload area is the one that we want to maximize in order to accommodate several different types of payloads. The idea is to generate a common structure for several different missions, whether with different payloads or on different rockets. We have generated a particular process for this, which I'm going to go and describe in details. But the important aspect is to be able to perform a single analysis on structural dynamics for this satellite takes a certain amount of time and effort. And to create a multi-objective optimization, we need to do thousands of these. So you can understand complication times thousands is a lot, but I want to focus on what it means in practical terms. So if we go on the next slide. Now imagine that you are organizing a weekend away with your best friend. It's going to be a piece of cake. You book the flights, you book the hotel, you book the activity. Even if you don't book something super cool, but it's your best friend, you're going to be happy. Now imagine that the purpose is to make happy a group of 20 people, some of whom you don't even know. So when you have to start organizing the trip, it's not going to be the same. You're not going to use the same approach. imagine just getting paid for all the flights, and everybody's going to moan about something. So trying to organize this is going to take a different way of approaching the problem and a different way of doing things. This is very similar to what we have to do now. So if we go to the next slide and the next one. So the first thing that we do is a finite element model. For those who are not familiar, it is basically discretizing a structure in tiny little elements, and then you apply all of your loading, whether they're forces, pressures, or thermal loading. And at the end, what happens is that you are able to understand in each individual element what stresses, forces, deformation, acceleration, etc. you're going to get. And of course, if your stresses, for example, are past the material allowables, it means you have a failure, you have to go back to the board. Now, to create this type of element, a finite element model, if you had a single standalone analysis, it would be fairly easy. But here we had to design it and to create it, thinking that we had to automate it. And we didn't automate it using a graphical user interface. So your weapon of choice, your standard finite element tool, but we were doing everything using input files. So the more traditional way of using finite elements. Next slide. Right, so we had to apply a different type of loading to this structure. So shock analysis, which is basically a strong acceleration in one direction. You can imagine when you have the deployment of the satellite, that is a huge acceleration for a limited amount of time. Frequency response, which is basically how the structure reacts to certain impulse of frequency. To give you an idea on this one, in 1985 in Mexico City, there was an 8.0 Richter earthquake. All buildings between 6 and 15 were heavily damaged. Above 15 floors and below 5 floors, they were pretty much intact. And the reason is that it doesn't really matter what materials you use or the philosophy of building. It matters the geometry and the distribution of masses. So it is less intuitive to understand how these structures behave and how to modify the design in order to cater for a different type of loading. Random response is when you're driving a car on an uneven ground and you don't have a repetitive type of loading, but you have to try to understand a type of loading over the course of the time. And when you apply it, what happens is that you're going to get an idea of the maximum type of stresses you may or may not get in a statistical way. And this is used predominantly in FNDT, but we're using it also here to identify the peak stresses. Next slide. And the next one. Okay, yeah, this one. So the initial FEM is then automated. What we do is we create thousands of initial models. So you could have the one and the next one has just one face that is made of a different material, or we can go down to changing all of the layup, all of the honeycomb panels, different dimensions and so on. You can imagine that if you have to do it manually, maybe it will take you just 10 minutes, but then you have to look at the output. But then some may take you a day. So when you sum up 10,000 of them, we're talking years of engineering work, and that's a lot. Now, we run each individual model through the same type of analysis and the same input loading that I described before, and then we have to look at the results. The next slide. This is an example of parameterization of our FEM. Each dimension is parameterized, so we don't touch anymore the graphic interface. All we do is to put a spectrum of value inside, and all the FEM is automatically generated. Next slide. Another important criteria is the center of gravity. When you have a large payload bay in a rocket, you have to respect a certain location of the overall CG for all of the payload. If yours is just part of them, you have to respect a certain volume of space for that one. So we discard anything that is not in line with the expectation of the rocket launcher management. Next. Now, each of these analyses is time dependent, which means that we have a result for each time step, and we have a lot of time steps. So the bottom line here is we have huge amount of output. We have reduced them to the core. We tried different file format to be able to reduce the size, but still this is something you have to take into account when you do the overall optimizations. There are ways that we employ. So we go through each individual file, extract only the information that we need, put them into our software, and then eventually perform an optimization. Next slide. So we are using a multi-objective optimizer actually, next slide. Actually, go back to the multi-objective optimizer. So there is a missing image. But anyways, in a multi-objective optimizer, you can optimize several different things. So this is not just about maximum stresses, minimum weight, or minimum volume. You can add anything you want. You can put the cost of the satellite. You can put the lead time if you have information on the manufacturing. You can put something like radiation shielding of individual materials. The sky is the limit. You can put as many objectives as you want, which means that this is like a topology optimization on steroids. And the purpose to do so is to find the sweet spot in the design space that will create a single design that will accommodate different missions, different payloads, and different rockets. Now, if we go to the next ones, to the risks. Now, there's a problem with optimization. It can be very risky because if your initial input are not very correct or well defined, there is even a small variation in the input loading, what you have optimized may break. It may not be satisfying. So what we do, instead of giving a design point, we give a design cloud. So we go into the center of this design point, meaning all of the dimensions are defined. And then we do sensitivity studies with a final, more in detail model. This is to really reassure that the safety is always guaranteed. Now, one of the important things is, in order to do this, you need an HPC or a powerful computer. It's very easy to go even online and get cores out of certain services. The problem is that, like I had problems with Teams today, or when you never manage to connect your scanner to your computer, when you have to deal with several different type of software, thousands of complicated analysis, if something goes wrong, it's very difficult to be on your own. So luckily at CFMS, we have a really good engineering computer services team. So every time we have a problem, my colleague John, is not very happy, but he's always able to solve it for us. Large storage, so much output size data that you really need to think carefully. And the other thing is, one size may not fit all, which means you may find a solution that fits all of the criteria that you wanted, but it's a little bit stiff. It's not very agile. This is like for the example of the trip abroad. This is eventually you go and watch COTS, but the movie, not the show. So you just settle on something that is mildly disappointing for everybody because it was the best choice. So one thing that you can consider when optimizing is maybe instead of optimizing for 4 different rockets, maybe we go for 1 or 2 and several missions, and eventually you're going to get a baseline of 3 or 4 satellites as opposed to 1, but they are way more optimized and maximized for the purpose. Last slide. So we have an amazing model-based system engineering team. They always come up with really clever stuff. One of the things is a new way to introduce the loading when it's frequency dependent, which we are probably going to utilize in a subsequent project. Our amazing colleague Robin as well has created a tool to simulate the radiation shielding of objects. This is something that is a plugin that we can put in for space applications, for example. Obviously, we're producing a huge amount of data. So what you can do is to create a surrogate model using AI algorithms or any type of algorithms that your data science team may want. And finally, you see at the bottom there are 2 images of a wing. This is the project DOS that James was talking about. We're using a similar approach for an automated wing. The purpose is conducting an analysis on applied air elasticity using a fluid structure interaction surrogate model. This is basically you have your weekend away and you have your in-laws as well. So it becomes extremely complicated. But the beautiful bit is that we are exchanging tools from DOS to the OSSAT project, because they have a slight different point of view. One is pure space, one is pure aerospace, and it's nice to create different things and then mix and match. This is all. There's a Q&A eventually, but if you're curious about this and you want to know more, because I had to go really quickly, just drop us an email and we can discuss.
Awesome, lovely. Thank you so much, Davide and James. That was brilliant. And I was just going to say the work that we've been doing with you guys has been really fascinating for us to see how it all comes together. And I'm sure we can there'll be some more detailed material that comes out that we can share with people as well, because it's been fascinating, and looking forward to seeing how the optimization goes and what we end up with. So no, that's great. Lovely. So Richard. Is it possible, Di, if we do them at the end, just because I'm conscious that some people will need to dip out, and we've still got a couple of presentations to go to.
Yeah, that's right.
Cool, thank you. So Richard, if you're ready, I'll hand over to Richard Tate, who's one of our individual collaborators, who's been doing something that's kind of quite nicely links in with this. So Rich, if you're ready, I'll hand over to yourself.
Thanks, Vicky. Just share my screen. Can everyone see that? Hello?
Yeah, that's
Can anyone hear me? Yep.
Yep.
Cool.
Yep.
Awesome. Brilliant. So, so I've been doing something that I wonder if I can maximize this. Is that maximized for everyone?
It's looking good.
Yes.
Awesome. Okay. Great. Yeah. So I've been looking at something. I think you said links in quite nicely. So this is how each launch vehicle has a separate envelope that is given for the payload that it can carry. And basically, we want to be able to launch on as many different launch vehicles as possible. So some analysis needs to be done on to kind of find a sensible envelope for OSSAT and to kind of whittle down which launch vehicles make sense to launch on. I've done some analysis on that, and also made some tools which will help us do that, and also help in the future when we're actually starting to do the preliminary development of the structure. So why is it important? So the harshest mechanical environment is experienced with spacecraft during launch. And I think, as Davide mentioned, there's some key different kind of envelopes environments that they experience. So you've got quasi-static loads, which is like kind of low frequency load, static loads, and low frequency loads, random vibration, acoustic loads, and shock loads. These are really key when you're doing the preliminary design and also the verification, because you need to actually test and qualify all of your satellite before it can actually launch. The launch vehicles that we've looked at so far are it's the Falcon 9, Electron, Virgin Orbit Launch 1, Alpha, ABL rocket, Soyuz, and Vega C, all of which have flown varying amounts. So what I've done is essentially try to overlay the envelopes for each launcher, which has its own challenge, because we don't really know, because OSSAT is being designed to be reconfigurable and have various different configurations, that for different payloads, while the actual platform's going to be as similar as possible, payloads not so much. So this means that there's going to be a large mass range over which an envelope must kind of assume, and also again, different launch vehicles, different subsystem configurations, and like for the acoustic envelope, you can have different areas of paneling and stuff, which will really change the loads that you'll experience. So for the quasi-static loads, first one I'm going to look at, you can see that there is some large variation. So here's all of the launchers, corresponding colors show the envelope for each one. Now, there isn't a complete write-up that accompanies this, because again, different masses are assumed in different ICDs and user manuals. So this is a really high-level snapshot and a very good way of looking at it, but there are caveats. So again, steady state and low frequency loads, and handling loads as well. And this really is useful for sizing the structure. So not secondary components and stuff, but it's really like the backbone of the spacecraft that it's useful for kind of designing. So random vibration, again, varies by mass of spacecraft, but these tend to be the ones that are applicable to the mass range that OSSAT is looking for. And different launch vehicles are split down into different launch configurations, because again, these can have different random vibration environments. I think it was similar to the quasi-static loads as well. Yeah, so these different mounting orientations for the Vega rocket mean that you're going to have some fairly substantial different loading. So yeah, you can see the GRMS, which is kind of a high-level look at the intensity of the random environment that it's going to experience. So again, yeah, this is all just stuff that's not repeatable launch to launch, but statistically is going to be the same between launches. So you got your acoustic end. So this is kind of the sound that is really like that gets impinged on the outer paneling of the spacecraft and can kind of reverberate around the fairing on the spacecraft, and has a completely different kind of load path because of this. So different launchers have, again, as I said earlier, different amount of, well, have varying amounts of launchers under their belt. So there's varying amount of information available, which again adds another layer of complexity when comparing these. So and some just give like a overall kind of envelope through the complete frequency range. So that's another challenge that we really have to take into account. We haven't got around to actually pinning down which launchers are going to be used. That's got to be done a bit later, but yeah, this is just the preliminary analysis so far. So moving on to shock. So this is things like separation events. So we've had a really preliminary kind of set of separation systems, and each launch vehicle will use slightly different ones. Also separation events between stages. So while these all look kind of similar, because this is a logarithmic scale, they're actually quite far apart. So yeah, again, there's going to need to be a line drawn where each launch vehicle, a line drawn at some point. So some launch vehicles are going to be kind of outside that limit. So again, I think Davide touched on this earlier. Center of mass, really important. It can actually affect the dynamics of the launch vehicle. So this is another thing that ICDs and launch manual user manuals will provide. So you can see that some that are really fine, while others that tend to have a larger payload carrying capacity will have a larger envelope. So yeah, again, we're going to have to form a sensible envelope for the whole OSSAT solution. The tools, I've made a few tools primarily in Python, but I've compiled these into executables so that anyone can use them. So this will be particularly useful for the Designathon. So the center of mass finder plotter, which you can see on the screen here, allows you to really just form solutions pretty much like Lego. Say, oh, what happens if we put the avionics box here? What happens if we put the solar panels here? And then you'll be able to compare that to the envelope in the previous plot, the center of mass envelope, and just see if it fits within the configuration that, or yeah, the envelope that we've decided. So yeah, all of these use config files, so you can literally just slot in new launch vehicles, slot in new envelopes, and it will automatically kind of plot and calculate the envelope for you, and also plot the center of mass. And yeah, hopefully it'll be useful to people in the team. So yeah, thanks for listening, guys. I'll hand back to Vicky.
Awesome, thank you very much, Rich. It's great, and as I say, like Rich said, we will make all these available so people can take them away, can try out different things, can see how they look, and so on and so forth. And it's been, I think it's been interesting to kind of see some of the challenges, but also we were surprised in some instances how similar some of the launch vehicles actually were. So maybe our ground plan of having it's close to one. We maybe a couple of structures isn't quite so out there as we might have perhaps first thought. So yeah, so we're looking forward to carrying that work on. Like Rich said, it'll be a good stepping stone for some of the Designathon work on the structures. What I'm going to do now is pass you over to my colleague Paul Madel, who's going to talk a little bit about, we're changing gears a little bit now. I'm going to talk a little bit about radiation and a little bit about software, just to kind of give you guys a flavour of some of the other bits and pieces that we've been doing. So Paul.
Thanks, Vicky. Right, I'm going to go through the same palaver of trying to get PowerPoint to do something sensible. Let's see how we go. Can we all see what I'm doing now?
Yes.
Yes.
Fantastic. Okay. Right, well, I'll crack on. So 10 minutes just to run through this, try and be as quick as I can. But this is just kind of an overview of what we're doing software-wise on the open source satellite, and then talking a little bit about some radiation testing we've been doing, and the results that we have now published on our website. So when we first started the open source satellite project, we got going on the software pretty quick, because I think our chief engineer was concerned that software is always left to the end, and we wanted to be up there quite up front and do the necessary research and the things to make things robust and sensible from the out. So we looked around at operating systems, we found various ones, and we decided upon FreeRTOS as one that looked like a good place to go. It's got some flight heritage on various spacecraft. It's quite simple. It's got a small footprint, but it doesn't have a particular feature that we really wanted, which was to be able to upload new tasks and run them and link them dynamically at runtime. So FreeRTOS doesn't do that. And it was a pretty nasty, in the weeds kind of problem to solve. But we have, luckily, a very capable collaborator, Anshul Makar, who's been looking at that. So he's been looking at trying to find ways to allow us to upload bits of code and execute them without having to take down the spacecraft and then upload and then get it going again, which is a bit disruptive from the operational point of view. So that's one application that we're sort of developing at the moment. We're doing that alongside the founder of FreeRTOS as well, Richard Barry, who's been helping us out along the way as well. And at the moment, we've got it running on a ChemU sort of simulated processor. And then Anshul's now looking to try and migrate that over to a real target, and we'll be demoing fairly soon the thing running on real sort of embedded hardware. Then we have CCSDS implementation. So we're trying to come up with an open source solution or implementation of the CCSDS communication stack. So CCSDS is something that's been around for a long time. It's a sort of multinational effort to try and standardize the way that we talk to spacecraft, whether they be in low Earth orbit or way beyond that. So far, we've got a implementation of CFDP, which is undergoing some tests, and Richard Tate, who is not only a bit of a sort of expert when it comes to mechanical stuff, is also helping us out there, as well as Andy Dax, who is our collaborator, who's based in New Zealand and is sort of writing the code. And at the moment, he's trying to, as Anshul is, to take that from a Linux-based sort of implementation and then getting it onto real hardware running on, our embedded target of choice. So that's what is going on there. Then it's all well and good having all of this kind of embedded software that runs, on our spacecraft, but it would be good to have a way of talking to it. And in the short term, we wanted to develop a simple application that could talk to our spacecraft as if it was in orbit. So, sending it telecommands, getting data down from it, telemetry data. And so we came up with a spec for this thing we're calling Mercury. The last time I presented this slide, it was a wireframe, you know, of what it would look like. And this is the actual version now that we're going to be releasing within the next week, release 1. And then we've got more collaborators lined up to sort of take that on going forward. I want to say thanks to Jamie Bailey, who's been you know, working on that, as well as Ricardo Mota, who's been involved with the graphical user interface design. And we've got other collaborators who are moving on to help us make that more capable. So as well as doing what it currently does, which is like a graphical user interface, we're also hoping to strap on a web API that will allow us to get collaborators all over the earth to be able to log in and send our satellite, you know, telecommands, try things out, see if their software's working correctly, that kind of thing. And not only that, we're hoping to integrate that into a continuous integration environment as well, which I'll explain a little bit. So if you end up, you know, working on our embedded software, then the kind of environment that you expect to see is STM Cube, which is ST Microelectronics integrated design environment. You can write code in it, you can compile code, you can debug on targets and stuff like that. So that's what we're using. And then we've also developed our own fork of QEMU, which is a simulation package. So you don't even need real hardware to actually execute the code. You can run code on a simulated bit of hardware through QEMU, and we've developed our own fork of QEMU to allow you to do that for our specific target of choice. And then that all hooks into what we've been developing from the perspective of continuous integration. So that's the kind of a buzzword with software type stuff, type people. But basically, you develop your code in STM Cube, you check it into, or you know, commit it to GitHub, and at that point we've got things set up. So now we've got this thing called Jenkins, all open source stuff, all of this stuff. But basically, Jenkins comes along and says, right, you've changed the code, right? Oh, okay. So I will now get that code out and compile it using GNU compiler. Not an actual, is that a RAM? I don't know what that is, but anyway, whatever that is, it's the logo for GNU.
It's a GNU.
So the GNU, it's a GNU, right? Okay. So yeah, it is a GNU, and that then goes along and takes that code and actually loads it onto a real target in our Farnborough lab. So you can be a collaborator anywhere in the world developing code, and this will happen, and it will run code on a real target in our lab in Farnborough, which then spits out test results using CMOCA and another tool as part of GNU called GCOV, which allows us to see how much of our code has been tested and how confident can we be in this code that we're developing. It gives you code coverage kind of analysis results, and then all of that gets you get notified at the end of that process via a little sort of notification in our Microsoft Teams channel, which is all quite funky, and I hope it works well. And then just to go on a little bit of a sort of sidetrack, really, with what's been going on. Cool, in terms
you've got kind of 2 minutes.
Oh, right, okay, I'll be very, very quick then. So we've been testing various sort of microcontrollers to see how well they stand up to the space environment. These are they. And basically, we took them to Guildford, to the Surrey Space Centre, tested them in a radiation chamber, and alongside the University of Surrey. And the results are basically they all passed the test. We wanted to see if they could withstand 10 kilораds of total ionizing dose radiation, and they all did. And we tested 4 of each. And all of the results are available on our website. So if you want to see the results, 40-page documents of why we chose those processes, what kind of testing we've done, what the results of that testing were, it's all documented there for you to read. And thanks to the University of Surrey for that, for the Sprint funding project that allowed us to fund that work, and from Mauricio de Carvalho, who's one of our collaborators who helped us along the way. And I just want to say thanks to all the people who are collaborating with us, volunteering their time to work on the open source satellite from a software perspective. So I think that's everything. And I'll stop there. I'll hand back over to Vicky. Is that right?
Yep, lovely. Thank you so much, Paul. Right, guys, I promise you I only have 2 slides left. I knew I was going to be down to the wire, so I say I'm not going to keep you, but I just quickly want to run through in effect what I'm calling all the rest, which hopefully will appear on all of your screens.
Mm-hmm.
Lovely, excellent. So we've talked today about mechanical, we've talked today about software, about radiation testing and the like, but that is not the totality of it. If you look at that and go, well, hey, they're not really my bag, don't worry. We probably have a little sticky note here or there that you might like to get involved in. So the backdrop here of this this slide shows our kind of notice board that we're running, which has lots of different projects on, which cover all different disciplines. So, we've got things from mechanical and software, but we're also looking at electronics. We really want to start looking at kind of doing some de-risking design work around some kind of circuit elements. So looking at, for example, power systems. We're going to need power systems for 25 kilo satellites all the way up to 250 kilo satellites. And as you can imagine, probably 250 kilo satellite going to want to touch more power than the smaller end. So we want to know, you notice a theme here, how do we do scalable and modular power systems, much like we want to do scalable and modular structures and other things as well. So there's lots of kind of interesting sort of electronics problems to get your teeth into if that's something that's of interest. We've also got bits around communications, actually looking at that whole ground space infrastructure, because we're going to have our open source kind of platform up there, but wouldn't it be neat if there was some kind of open source ground elements that we could use as well to really help open up that whole chain? We've got a bit here around kind of algorithm developments. How do we actually make the satellite do what we want it to do and point where we want it to point? All those useful things that people kind of expect. So we've got some interesting things there. So kind of if you're into kind of control and algorithm development or maths, it's lots of maths, but that's something else that you might want to kind of consider. We've got testing and validation, and Paul showed a little bit there about continuous integration and how we kind of do that from a software perspective, but we also want to look at how do we test what we're going to generate on the ground. We don't want to launch one and then find we've got some problems. We want to do as much as possible which is representative to flight actually here on the ground. So what can we do to kind of set that up? And we've also got systems. I'm a systems engineer, so it's my my favorite area, but what does it actually need to do and how are we going to get it to do it? And these are all still areas that we're working through, and there's loads more being added all the time. And I must say these kind of lists are very much determined by kind of the collaborators that are around at the time and kind of what people's interests are. So we're willing always to discuss new project ideas and see if there are things that we can get added on. Now,
and that's at an individual level as well as a corporate level.
Oh, yes,
if you're a team and you want to get involved, or if you're just you just want to do it as an individual contribution, both of those options are open.
Indeed, thank you very much, Anita. That's a good point. So this is my wrap-up slide with sort of 30 seconds left, so I will quickly whip through this. Just want to reiterate kind of what Paul and the others said. Thank you so much to our collaborators, the ones today who've given their time to kind of present to you guys, and also the ones you haven't seen today who are behind the scenes kind of working away. We all feel every time we get to speak to our collaborators, it gives us a real kind of sense of enthusiasm and kind of vigor for the project, and it's nice, it's great for us to work with people who are also so passionate about wanting to do things which are cool, but also things that are actually going to fundamentally hopefully change the way the space landscape looks. And so I want to really say thank you. We couldn't do it without you. As we said, all the material from today's session will be made available on our website, and in good old streaming fashion, you'll be able to watch this on demand. So if you know someone who might be interested in something we've talked about today, spread the message, spread the word, get them to kind of put us on repeat and check us out. And if something you've seen today looks interesting, what I can recommend is you register your interest via the website. You'll then get an email from myself, Paul, Ben, or one of the other members of the team, and you'll get to see our wonderful faces again as we give you a welcome video call. And once we get you all signed up, away we go. We can then kind of look at what we want to do together and crack on and do some really interesting and fun work. So it just leaves me to say thank you very much again. And here are some of the details for getting involved. But we'll make these available after the session so everybody can get them and haven't got to kind of hurriedly write them down now. So I think that brings us to the close of the session. And what I'm going to do, Anita, if it's okay, I'll hand back over to yourself and to let you close out today.
Brilliant. Thanks to everybody. That was such a great overview of so many of the activities that we're working on. And as Vicky showed at the end, there are so many more that we still want to pursue as we work towards the development of the world's first open source small satellite. And so there are lots of areas to get involved. If you're already involved and you see something that you want to get involved in that you're not already involved in, you know, it's a great opportunity to kind of get more experience and more exposure, either at an individual level or at a corporate level, such as the work we're doing with CFMS. That's a really excellent example there. So if you think that there are things that your organisation might be involved in, getting involved in, and just, you know, really as a pilot to see how open source could work for you and how you can leverage what we're doing into your own projects and programs, then it's a conversation we'd really be open to having with you, just to talk about the philosophy and the principles and how we want to just grow the community and share the work that we're doing and allow everyone to benefit from that. I'm sure some people have got to drop away because it's past, but I'm willing to stay on the line. I'm sure a few other people are. If you've got questions that you want to ask, we can carry on the conversation for another few minutes. If anyone wants to stay on, please hang around. And if you need to drop off, I'll say thank you and good night to some of you maybe, and good afternoon to others. And I hope you have a great rest of the day.